Welcome to this explainer. We're going to dive right into exactly how massive structures are designed to stay standing. We'll be taking a really fascinating journey, literally starting from the microscopic atoms of steel all the way up to the macro-scale math of skyscrapers. If you've ever looked up at a towering skyline and wondered about the hidden science holding the whole shebang together, well, you are absolutely in the right place.
It really comes down to a fundamental question. What actually keeps a skyscraper from tumbling down? How do we harness steel, a material that's roughly 10 times stronger than concrete, to build our modern cities safely in a highly unpredictable world? Wind, earthquakes, and immense physical loads are constantly battering our buildings. So today, we're going to decode the engineering and metallurgical secrets that make these modern marvels possible.
So, here is our roadmap for the journey. Section 1. The ultimate building material. 2. The secret life of steel. 3. Forging strength and ductility. 4. Pushing to the limit. And finally, Section 5. The science of safety.
All right, let's jump into Section 1, the ultimate building material.
Look, before a single beam of steel is even cast, a structure begins with a literal dream team. The owner approaches an architect who plans the layout to satisfy functional needs while making sure the building is aesthetically pleasing and, of course, economically feasible. But the architect doesn't work in a vacuum. They hand that plan over to the structural engineer. The engineer is the one who locates the structural elements to ensure total safety and serviceability without ruining the aesthetics. Finally, the contractor steps in to actually fabricate and erect those elements. So the absolute crucial point here is that a safe, useful, and beautiful structure is only born when this entire team collaborates seamlessly, fully understanding what each other brings to the table.
And when this team decides on materials, steel is often the undisputed champion. Just notice the sheer advantage it has over concrete. With approximately 10 times the strength, steel offers an incredible strength-to-weight ratio. This makes it incredibly economical for really tall buildings and massive, large-span bridges. Plus, it allows for much faster construction times, meaning the building can be opened and used earlier. On top of that, steel is super ductile and robust. Those are the exact qualities that allow it to withstand severe, sudden impacts, like earthquakes. Add in the fact that it's highly eco-friendly and easily dismantled and recycled as scrap at the end of its life, and you can clearly see why its overall life cycle cost makes it the ultimate choice.
Which brings us to Section 2, the secret life of steel.
At its most foundational level, steel is simply iron with a tiny dash of carbon added in. But the magic is really in how they mix. The atomic diameter of carbon is actually smaller than the gaps or interstices between the iron atoms. Because of this, carbon dissolves into a solid solution, literally squeezing right into these microscopic gaps. And by doing so, it physically distorts the original crystal lattice of the iron. You can kind of think of it like wedging tiny blocks into a sliding puzzle. These carbon atoms mechanically block the crystal lattices from dislocating or sliding past each other when a force is applied. That microscopic mechanical distortion, that is exactly what gives steel its tremendous strength.
Now consider the iron-carbon phase diagram. It's essentially a cheat sheet for metal. As the temperature drops, iron takes on completely different forms. Depending on the exact amount of carbon, which usually tops out at around 2%, that blazing hot austenite cools down into either extremely soft ferrite or a much harder, more complex mixture that we call perlite.
Let's move to Section 3, forging strength and ductility.
Let's walk through the actual steps of slowly cooling a standard 0.2% carbon structural steel. It's almost like a race against time. We start at Step 1, with austenite at a scorching 900 degrees Celsius. As it begins to cool into a two-phase field, we hit Step 2. Ferrite starts to nucleate, forming tiny crystals right around the boundaries of the austenite grains. Because ferrite simply can't hold much carbon, that carbon diffuses away into the remaining austenite. Finally, in Step 3, as we cool all the way down to room temperature, that remaining carbon-rich austenite transforms completely into perlite.
We can picture this beautiful microscopic transformation happening in 3 distinct stages. First, you have the large austenite grains with tiny ferrite nuclei forming right at their borders. Next, those ferrite regions grow, effectively pushing the carbon inward. And finally, that center region becomes perlite. Perlite is a really fine lamellar mixture, kind of like a microscopic layered cake, made of soft ferrite and a hard iron carbide called cementite. The higher your carbon content, the more of this hard perlite you get. That means higher mechanical strength, for sure, but unfortunately it also means lower ductility.
Because of that eternal trade-off,
Engineers literally manipulate the cooling speed. If we use a process called annealing, where the steel cools very, very slowly in a furnace, the carbon atoms get plenty of time to shuffle around. This creates larger grains and a highly ductile steel. But what if we plunge that glowing hot steel directly into cold water? Well, that's called quenching. This rapid cooling violently traps the carbon atoms in place before they have a chance to diffuse, creating a crystal structure called martensite. Now, martensite is incredibly hard, but it's also very brittle. That makes it totally unsuitable for massive structural beams, even though it's absolutely perfect for something like high-strength bolts.
Okay, Section 4, pushing to the limit. To actually trust this material in the real world, we literally have to stretch it until it breaks, period. Think about a standard tensile test specimen. A massive machine grips those precisely machined shouldered ends and pulls in opposite directions, applying immense tension. Engineers carefully measure the stress and the resulting strain over a specific gauge length right in the middle. The steel will stretch elastically at first, which means it would snap right back to its original shape if you let go. But eventually, it hits a yield plateau, goes through strain hardening, and is pulled apart entirely. When structural steel does finally fracture, engineers are hoping to see a very specific signature, a cup and cone fracture. This is where one broken end forms a cup shape and the other forms a cone that fits perfectly inside it. Why is this so vital? Well, a cup and cone pattern proves that the steel suffered a ductile fracture. It means the steel deformed and stretched significantly before failing, giving us plenty of warning, rather than just shattering abruptly without warning, like a pane of glass.
Beyond just stretching it, we also need to test how well the steel resists scratching and denting, its surface hardness. We do this by literally forcing an indenter right onto the surface of the steel and measuring the microscopic dent it leaves behind. The Brunel method uses a hardened steel ball, while the Vickers method goes with a square-based diamond pyramid. By taking the exact ratio of the applied load to the tiny surface area of the indentation that's formed, engineers can calculate a highly precise hardness number.
And that brings us to our final part, Section 5, the science of safety.
Modern structural design operates on a really brilliant philosophy, developed back in the late 1970s called the limit state method. A limit state is simply a threshold, a condition where a structure fails to fulfill its intended purpose. And there are two main categories we look at. First is a limit state of collapse. This deals with catastrophic failure, things like metal yielding, crushing, or buckling. We require massive, non-negotiable reliability here because human lives are on the line. The second is the limit state of serviceability. Now, this isn't about the building falling down. It's just about normal, everyday use. If a skyscraper sways so much in the wind that it causes massive deflection, or vibrates so much that the people inside literally feel seasick, it has failed its serviceability limit.
So, the absolutely crucial takeaway here is captured in one deceptively simple equation. FD must be less than or equal to SD. This is basically the ultimate blueprint for safety. FD represents the factored design loads. That's the maximum internal forces and moments caused by wind, gravity, and earthquakes. SD represents the factored design resistance, which is the actual physical strength of the steel itself. The forces pushing on the building must absolutely never exceed the material's capacity to push back.
But you know, the real world isn't perfectly predictable. So how do we actually factor in those chaotic variables? Well, the major innovation of the limit state method is the introduction of partial safety factors. Instead of just throwing out one big, clunky safety net, engineers split the risk using probabilistic math. For example, when calculating the strength needed to hold up the dead weight of the building plus the live load of people and furniture, engineers will multiply that expected load by a factor of 1.5. That extra buffer accounts for things like extreme weather or totally unexpected overcrowding. Meanwhile, a completely separate safety factor is applied to the steel's strength, just to account for any tiny unforeseen manufacturing imperfections in the metal itself.
It is just absolutely remarkable when you step back and think about it. Our tallest, most imposing structures are ultimately kept standing by probabilistic mathematics predicting extreme scenarios, all relying on microscopic atoms of carbon slipping perfectly into the lattice of iron. But as we continue to push the boundaries, building taller, bolder, and more complex structures in a rapidly changing climate, it leaves us with one final thought. If our safety relies entirely on predicting the extreme, what completely unknown limit state will tomorrow's engineers and architects have to design for next? Thank you so much for joining me on this explainer. I really hope this changes the way you look at the skyline forever.